I'm assuming you're watching this video because you don't quite understand partial differentials. Well, let's start from the beginning. Because differentiating a 3D graph is just as simple as differentiating a 2D graph, because it's essentially the same thing. Recall the formula for finding a slope, it's just rise over run. Since the graph doesn't wobble too much, the rate of change is constant, so it doesn't matter how far apart the points are, the rise to run ratio will always be the same. We don't have to take any limits. But when we don't have a slope or a constant average rate of change, we sort of have to take the limit as the change in x approaches 0, and then we get an accurate rate of change across the whole graph. It's great. When we start dealing with higher dimensions, such as this, we can't just take the limit of x approaching a point and say we're done, because we have more variables to consider now. What multivariable equations do is what single variables do. It's still the same thing, just for every single variable. We find how much it goes in the x direction, and the y direction, and the z, and so on. So let's have a look at this graph. Let's pick a point, and it has the coordinate x, y, z. X will go on its path irrespective of how y behaves. Of course, z is the dependent variable, so it is a result of how x and y decide to behave. So if you just figure out the rate of x and y, you'll figure out the rate of z. So we're not just finding out how fast x changes, but also y. We have more than one variable changing, so we just find out how fast each individual one is changing. One way to visualize this is by building a sphere piece by piece. So let's plot 0, 0, 0 first. Now 0, 1, 0, which is just up 1 on the y-axis. Let's go left by 1, and let's go back into the screen by 1 to represent the z-coordinate. You know, all the function does is automatically build a sphere for us, so we don't have to dot the whole thing. It knows all the points. So if we partially differentiate a function, we partially differentiate every single point, which is the most amazing thing ever. So we've built our sphere using a function. We didn't dot everything. I'm sorry guys, I'm not going to do that. So each dot is a result of some distance along each axis. So some distance along x and along y, and that gives us our z. So when we differentiate an equation and hold all of the other values constant, we restrict the movement of that dot with respect to its y dimensions, so we can find the rate of change in the x direction without affecting the location of this dot. If we didn't hold y constant, we would not be finding the rate of change at any fixed point. It would just be I don't know what would happen, but it wouldn't do what we'd want it to do. So we condense this entire concept into this symbol, and it doesn't really have a special name like lambda or epsilon. It's just d or curly d, and there's the history at the bottom if you want to have a look. So to summarize, partial differentials find the rate of change in all axes directions, not in between or southeast, either x, y, z, or however the axes are defined. So differentials do this as well, just with less variables. So now, with this concept, think about it, if you partially differentiate our y equals x squared, what are you going to get? You're going to get 2x. I thought I put it in here, I didn't. Must have been some other video. But yes, I hope that makes sense, and feel free to send any questions. Oh, and good news, this continues across all functions, no matter how many variables there are. Just hold them all constant, except for the variable you want to find the rate of change of. Thanks for watching, guys.